Antiferromagnetic materials. In the case of antiferromagnetic materials, the adjacent dipoles are aligned in anti-parallel manner. Okay, so this dipole is pointing in this direction. The adjacent dipole is pointing in the opposite direction. So the adjacent dipoles are aligned in anti-parallel manner and the magnitude remain the same. So that is how we call it as antiferromagnetic material. So the properties of antiferromagnetic materials are the adjacent magnetic dipoles are aligned anti-parallel direction and magnitudes remain the same. Susceptibility is positive and the susceptibility value is small in the case of antiferromagnetic material. Then just see the graph, temperature along x-axis and susceptibility along y-axis. As temperature increases, susceptibility also increases and reaches maximum susceptibility at a temperature called Néel temperature Tn. Once Néel temperature is reached, still if we increase the temperature, the magnetic susceptibility starts decreasing. So Néel temperature is the temperature at which the susceptibility is maximum in the case of antiferromagnetic material. So below Néel temperature, susceptibility increases and above Néel temperature, susceptibility decreases. So we say that when T is lesser than Tn, that is this portion, we call it as antiferromagnetic material. When T becomes greater than Tn, this portion, the material becomes paramagnetic material. So these are the properties of antiferromagnetic material. Examples of antiferromagnetic materials include chromium at room temperature, manganese oxide, manganese sulfide, chromium oxide, nickel chromide, etc. Next, ferrimagnetic material, otherwise known as ferrite. So if we see the dipole alignment, adjacent dipoles, they also point in anti-parallel direction, but their magnitudes are different. So see here, from here to here we have, but if we take the adjacent dipole, the magnitude is going to be different from this one. So the properties of ferrimagnetic material include the adjacent dipole moments are aligned anti-parallel direction and magnitudes are different. It has net magnetic moment. The susceptibility is positive and it is very large. They have high permeability and high resistivity. There is a low eddy current loss and also there is low hysteresis loss in the case of ferrimagnetic material or ferrites. Usually ferrites, if sum of iron oxide and metal oxide, we call it as ferrites. So to summarize, just see the spin alignment. So in the case of paramagnetic material, we have random spin alignment. In the case of ferromagnetic material, all the magnetic dipoles are aligned in the same direction and the magnitudes are also same. In the case of antiferromagnetic material, the adjacent dipoles are aligned in opposite direction but their magnitudes remain the same. So when we consider ferrimagnetic material, the adjacent dipoles, they point in opposite direction and also their magnitudes are different.